Okay, let's go ahead and start the class. A couple of things before we talk about the lab. Just one thing actually. I've added all of you to the same section on Blackboard, so some of you may see two Aerospace Lab 1 in your Blackboard. The one that says AESP T61002, which stands for section 2, that's the one I'm going to use, right? Okay. So the other one can just delete from your Blackboard. I mean, if it annoys you. If not, then you can just keep it there. And all of the material, everything will be uploaded on that one. All of the announcements will be made on that one. If you were part of the section 1 and you can't see the section 2 in your Blackboard, let me know, right? Because if you don't, you're going to miss all of the announcement and all of the documents, right? Does this make sense? Yes. It's clear for everyone? Okay. So today we are going to start talking about Lab 1. First thing you want to do is to go over the lab instructions, Lab 1 and 2, and this lab instruction is already uploaded on Blackboard. You can have access to it. And Lab 1 and Lab 2 are essentially the same lab. It's just we're going to do two different things using the flight simulators. The idea of Lab 1 and Lab 2 is for you guys to learn how to use the flight simulator first, then understand the different parts of flight mechanics, how different flight controls are going to control your plane, how much speed do you need to be able to take off, or what is the landing condition, all of these things. And that's a practical thing. If you don't really have enough speed, enough energy, you won't be able to take off. If your landing is not very well thought of, you will destroy the plane, and so on and so forth. So hopefully not I mean, unfortunately, no one will get hurt if your plane doesn't land properly. But it's a simulator, so you will get the point. You will understand how to fly a plane. So that's the goal. The goal is for you to, that's the first one, to understand how different control mechanisms we have on a plane will affect your flight performance. Right? The second goal is to understand the aerodynamics of flight a little better. At this point, I'm hoping all of you have passed aerodynamics, right? Okay, so you understand the lift coefficient, drag coefficients, angle of attack, lift versus angle of attack, drag versus angle of attack, and also the drag polar, which is CD versus CL, right? All of these plots you understand, and you understand the importance of them for an aircraft, or for a wing, or for an airfoil, right? So your second goal in the lab is to export all of these flight parameters, lift coefficient, angle of attack, all of those things, moment coefficient, everything, and plot them. CL versus alpha, CD versus alpha, CM versus alpha, and also CD versus CL. That will be the Lab 1. Usually people stay longer than the time of the lab because they want to play with the flight simulators. And as far as I'm concerned, I want you to use a Cessna plane, but if you want to use any other plane, you're welcome to do so. You just have to be able to explain the plane a little bit. All of the manuals for each plane can be found online for this specific software. So you can definitely use the plane, but flying those planes, flying more complicated planes is going to be more complicated, right? Flying a Boeing is not as easy as flying a Cessna, right? And that's true for real world applications. You had a pilot here, right? I assume you can attest to this, that flying a Boeing is harder than flying a Cessna. It's true in the simulator as well. And you also, this software also has a space shuttle, so if you want to use that, you can use that as space shuttle. Whatever you want to use, that doesn't really matter. But I have already uploaded the manual for Cessna 172 on Blackboard. You can have access to it. But if you want to fly any other airplane, you can do so. If you wanted to use the flight simulators at outside of the lab times or office hours, your lab TA's office hours, you can send me an email or send your TAs an email and schedule a time with them. So that will be this first lab. Second lab, as I said, we are going to use a different software. It's called the Playmaker. We are going to change some parameters of the plane you have already used, right? And see how that specific parameter will affect your flight performance, right? How it is going to change the stalling of a specific plane, right? And that will be the second lab. Mostly, that will be mostly the first and second lab. I'm thinking of adding something to this lab, which is going to be more work for you. I'm thinking of adding the calculation of the liftoff distance, which we will talk about in the lecture. But for each plane, for the plane you're going to use. But it is, I'm not sure. I have to see how much more work you're going to do. If it's too much work, then I will probably not do it. Is there any questions about the labs? No? Yes?
Is it one lab report for the two, or is it?
Yes, yes. It is one lab, so you're gonna have one lab report for the do, and you will be credited for 2 lab reports. That's because it's the beginning of the semester. I don't want to overload you. We already have 10 lab reports. This is a very time-consuming course. Not a very hard course, but it will take a lot of your time. Every week I have to write a lab. So the least I can do is to give you credit for 2 lab reports at the beginning of the semester. And what else? One more thing that I wanted to mention before this. I may need, because there is 33 of you and we only have 4 hours for the labs, I may need 10 of you to come to the lab at another time. So I may need to open up another time for the labs, right? And that other time I don't really have any TA for, so I'd probably do it myself. So who is flexible enough? Who's the schedule? I'm pretty sure all of you are flexible, but you don't need to show. I mean, you don't need to show your hand. Just send me an email if you could, if you are flexible enough. And then, I guess this is what I'm gonna do. I'm gonna send you the available times that we can do, and just all of you fill out the survey. I guess I choose the one with the most votes. Right, and we go from there. Okay. Okay. So let's talk about the flight controls. We have different control systems in an aircraft. The first one is going to be the flight control system, which will be the main topic of discussion in this class. We have cockpit controls that are the control that are inside your cockpit, like the steering wheel, the rudder control, all of those things. We have the connectivity linkages between the cockpit controls and the flight control systems that are on the plane themselves, and also some direction controls. We can group these flight control systems, the aircraft control system, into 3 main control groups. The first one is going to be the primary flight controls. The second one is going to be the secondary flight controls, and the third one is named auxiliary flight controls. We are going to talk about the primary and secondary flight control systems today and on Monday. And we will not talk about the auxiliary flight controls at all. And your lab is mainly focused on the primary flight control system, unless you want to make it a little more complicated for yourself and change a parameter that is not part of the primary flight controls. One thing I forgot to mention about the lab. If you, you have to change something about your plane that you have chosen, but you have to have a reason behind that change, right? Let's say you want to increase the lift for whatever reason, and you think changing the airfoil of the wing is going to increase the lift. It may, but you have to have an explanation. I did this change because I thought this would happen, and at the end of the lab report, I want you to make a conclusion. Was my assumption correct or not, right? Did I get what I wanted to get or not? Does it make sense? Okay. So, let's continue. Let's actually watch this YouTube video, this topic. This Flight Club, it's a YouTube channel. They have a lot of good videos on flight control systems. This is their
An aircraft is
explanation.
an amazing machine, capable of flying in any direction and rotating about in 3 dimensions. These are called axes of movement. The average location of an aircraft's mass is a point that is called the centre of gravity. So if you suspend an aircraft from the centre of gravity by a line like this, the aircraft remains perfectly balanced. Each of the 3 axes moves about the centre of gravity. The aircraft's principal axes are normal axis, drawn from top to bottom, lateral axis, drawn parallel to the wings, and longitudinal axis, drawn from tail to nose. Each axis is perpendicular to the other 2 axes. Let's look at each individually. The rotation about lateral axis is called pitch. This movement changes the vertical direction of the aircraft's nose. The rotation about normal axis is called yaw. This is the movement of the nose of the aircraft from side to side. The rotation about a longitudinal axis is called roll. This is the movement of the aircraft's wings. One wing goes up, the opposite wing goes down. So in summary, these are the 3 principal axes of movement.
You're going to hear these a lot in the first part of this course, and I assume your flight mechanics course, also the aircraft design course. So you have to be familiar with the nomenclature here, the names here, which I assume that most of you should be already familiar with this. Just wanted to make sure that we are. And here I also have a summary of what we had over there. We have the 3 main axis here, the longitudinal, normal, and also the lateral axis, pitch, roll, yaw. The primary movements of an aircraft, right? Well, how do we control the pitch of the aircraft? It is done through the elevator. An elevator is usually located on the tail wing. We'll talk about the elevator a little bit more. How do we control the roll of the aircraft? It is done through ailerons. Ailerons are usually placed at the end of the wings, 2 wings at the 2 sides. And how do we control the yaw of the aircraft? It is done by the rudder, that is usually on these stabilizers here. That's at the back of the stabilizer, and it's controlled by the movement of that, I guess, rudder control system. Okay. Any question about the movements of aircraft? Is there anyone who was not familiar with these things? Okay, that's good. Everyone was familiar. So elevator, let's just dig a little deeper in how the elevator changes the pitch of the aircraft. So whenever you have, whenever your elevator moves up a little bit, what's going to happen is that you are going to actually go here. So you have this tail wing, elevator is connected to this tail wing. Whenever this elevator moves up, you will have a downward force on the elevator at the tail of the wing, which means that the nose of the wing will pitch up, right? But the question I have for you is that why does this happen? Why the upward movement of the elevator is going to cause a downward force?
The difference in pressure?
Different pressure. Okay, how does this, can you elaborate a little bit?
So, like when the aileron is pushed up, the wing that goes on top of the tail will make the tail push it down, which will cause the nose to go up.
But how does it affect the pressure distribution on top and the bottom?
Oh, the distance that it will travel in the sense. I don't know how to like.
So what are we changing? Let me ask you this. What are we changing?
Are you changing the velocity of the air as it goes over the surface of the?
What geometrical parameter is changing here? Like, see, this is the regular effort. What I have changed? What have I changed here? You have to speak up.
Sorry.
Go ahead. Camber, right? So the camber of this airfoil is being changed by the upward movement of the elevator, right? And when you change the camber, what's going to happen is you're going to have a higher pressure location here, lower pressure location here, which is going to act in the opposite direction to a desired lift, right, on the tail. So it is going to push the tail down and push the nose up. So this will cause a pitch up. I'm sorry, I'm standing. My handwriting is already bad, so when I'm standing, it's going to be worse. So, and then the elevator is pushed up, pushed down. We are going to increase the camber, which means that the tail is going to be pushed up and the nose is going to pitch down. Any questions here? That's usually the case. Whenever it comes to primary flight controls, you are usually changing the camber. It is going to change the aerodynamic forces on the wing, on the tail, or whatever, right? On the vertical stabilizer, and then that will cause some sort of a movement, either roll, yaw, or pitch, right? That is always, and you're going to see that later on. So, but the elevator or the stabilizer here is a one-piece horizontal stabilizer. So all of it is on one piece. It's not like the wing that is installed at the two sides of the fuselage, right? It is just one piece at the tail of the wing that pivots from a central hinge point. And when you pull back your when you're pulling back the steering wheel, right? Let's make it a little more car-like. The steering wheel of the aircraft, you're going to pitch up. When you pull it away from yourself, you're going to pitch down. This is something you're going to see in the flight simulator, and I'm pretty sure you already know this. The thing is, this stabilizer is pretty sensitive, so we are going to incorporate something called an Anti-Servo Tab to decrease the sensitivity of the stabilizer, the elevator, to your command. So if it's too sensitive, with a very small movement of your controls, you're going to have a very high pitch up, pitch down mechanism happening, which is not necessarily ideal. And we said ailerons are going to control the roll of the aircraft. That's ideal. The ailerons are attached to the outward trailing edge of each wing and move in the opposite direction from each other. So when you have the aileron moving up in one direction, the other wing on the other wing, it is going to move down. Now, how is it going to affect your movement? Let's actually try doing this here. So let's say this is my wing. This is the top view of the wing. We have a fuselage in between. what will happen if this aileron moves up? This will move down. What will be the direction of the roll? In which direction? Counterclockwise? This direction? Can you elaborate on this? Can you explain? Whoever said that.
Pressure changes are opposite forces. Like there's a high on one side, on top, and lower.
So explain it to me with lift and drag. So what is happening here? It is moving downward. So we are increasing the camber, right?
Oh, it's going the other direction. That one's going down.
Does,
One.
this is going down, this is going up, right? Doesn't really matter. Just try to explain it. Let's say let's stick with this. What is going to happen to lift here? It is going. No, it will increase, right? That's the idea. So you're going to have a very higher force here. What is going to happen to lift in this direction? It has moved up on this wing, right? So your lift is going to decrease because we have some downward force acting on the wing, right? Does it make sense? So we will have a smaller lift. What does it mean? It means that your aircraft is going to roll in the clockwise direction. Does this make sense? Is this clear? But there's something else that is going to happen here when you are moving your steering wheel, right? Your stick. Your drag is also being affected. What happens to drag when we increase the camber of a wing? It increases, right? Because there is more surface area that is resisting the air movement, right? Your drag is going to increase, right? But the direction of the increase in drag is going to be different for the two top parts of the wing. So we will have higher drag in one of the directions, and we will have a lower drag on one of the wings. We will have lower drag on the other wing, which means that we are going to see, since drag is only happening in the, let's say this is the y direction, drag is only happening in the y direction, this difference is going to cause a rotating force in one of the directions, right? And that is going to cause yaw, right? But this is not something that we want. This is called the reverse adverse yaw. Thank you. Right? And we want to work on this adverse yaw. We want to try to minimize this, right? Any questions so far? And rudders are going to use to counteract the adverse yaw, of course. But the amount of this rudder control required is very dependent on the airspeed, also the angle of attack, and the aileron deflection. We have two types of ailerons. We have the differential ailerons that are shown here, and deflected up and deflected down ailerons. And we also have the freeze ailerons that you can see on the right side of the picture. We have the neutral, raised, and also the lowered one. Any questions so far? Okay. Let's move on. The next primary control system on a flight, on an aircraft, is the rudder control system. The rudders are controlled by the pedals, and essentially it's exactly the same thing. When you increase the camber in one side, you will have an aerodynamic force that is going to act on it, and is going to move the aircraft in one direction or the other direction depending on the change of camber in this specific location. Any questions? So, my expectations from you in the lab is to try to understand and learn this, the lab one. Learn this, how these primary flight controls are going to, how important they are in your analysis, in your flight. And you are going to be able, with whatever we have in the flight simulator, you are going to be able to control the elevators, the ailerons, as well as the thrust. I mean, that's a different discussion, as well as the thrust of the engines and also the rudder. So all three primary control systems can be controlled with whatever we have in the lab. But there are some things we can do to control the secondary flight control systems. The secondary flight control systems are essentially the control systems that we don't really need in an aircraft for it to fly, for it to control them. They are just there to optimize and enhance the performance of an aircraft. There are different types of them. For example, the leading edge devices, trims, and flaps. Leading edge devices, you can see examples of the leading edge devices here. Let me ask you one question. What is going to happen, or what does this leading edge device, the fixed slot leading edge device, do for us? Let's say you are flying, it is connected to your wing, and then you release it. So it gets a little further away from the wing. What is going to happen when I activate that, when I start using it, when that starts moving away from the wing? You already understand the ailerons or the flaps at the end of it. They essentially do the same thing. We already understand that they are going to increase the camber, right? Ailerons work in a different direction because the two on different two sides of the aircraft work in reverse, right? That's why you're going to see them roll. But a regular flap on both wings is going to move in the same direction, right? That's why it's just going to increase, decrease, or whatever, the lift and drag. Right. So that's the difference between aileron and flap. But my question still exists. What does this do to the aerodynamics of the wing? Yes?
It separates the flow, right? So on the front edge, you'll have some flow that's coming from the top, and then some that will kind of come underneath.
Yeah, that's correct, exactly. But what is going to happen? What is the important? What is the benefit of that? So, what is your name? Jackson. What Jackson is saying is that whenever you have this, this gets a little further away. In the regular condition, these are together, right? So you have flow in this direction. But whenever this slot moves away from your wing, this is the type of flow or streamlines you're going to see. You want to elaborate on that?
Well, I'm just kind of guessing. I can't quite remember exactly, but I mean, it has something to do with like increasing the amount of lift because it almost like creates another area where you can have like a pressure difference on the front. I could be wrong, but that's just what I'm thinking.
That may happen. That may happen, but that's not really the I guess the importance and the benefit, the enhancement it causes. Is there anyone? Yes.
It increases the core and helps delay the boundary layer separation.
It mainly helps delay the boundary layer separation. So what you're actually forcing, you're introducing this extra streamline in the flow. That means that your boundary layer is going to be suppressed a little bit. So it will delay the boundary layer separation. It will definitely enhance the lift, but its main job is to delay the boundary layer separation, which is then going to cause a lot of trouble, as you already know from your aerodynamics. So we talked a little bit about the flaps. One of the main function of flaps is during landing, because you want to increase by these flaps, you can actually increase the angle of descent without increasing the airspeed. Different types of flaps that you can see. We have plain flaps, we have split flaps, slotted flaps, and folder flaps, and slotted folder flaps. In your actually lab 2, which you are going to, most of you are going to take next year, you will have a numerical analysis in which you have to do a CAD design on one of these flaps and do some aerodynamic analysis using ANSYS, which I assume most of you will enjoy. So what are trims as secondary flight control system? Trims are designed to minimize the pilot's workload, or they essentially aerodynamically assist movement and position of the flight control surfaces to which they are attached. Common types of trims: we have trim tabs that can be adjustable and fixed. We have anti-servo tabs, we have balance tabs, and adjustable stabilizers. Different examples of trims, as you can see, they can be used on the elevator, and most of these examples are actually talking about the trims on the elevator. Any questions so far? Okay, let's talk a little bit about the landing and takeoff. So, or let me ask you this. I mean, you already saw this. To be able to be airborne, the lift produced by the aircraft must be at least equal to the weight of the airplane, right? If you recall, the aerodynamic forces what are the main aerodynamic forces that we usually deal with?
Lift, drag, weight, and thrust.
Lift, drag, weight, and thrust, exactly. And drag operates in the same direction as thrust. Lift operates in the same direction as weight, right? And lift is the force that is going to help you to be airborne, right? If you have any lift, then you wouldn't be able to be airborne at all. So, I think it is very understandable that to be able to fly, the force you are generating in the weight direction has to be at least equal to the weight, right? So it cancels the gravitational force of the Earth, right? The reason we can't fly is because of the Earth gravity, right? Is because of the weight. So if we cancel that force, become weightless, essentially, we should be able to fly, right? That's the idea. But we also have a condition for the velocity of the airplane. Its velocity has to be equal or greater than its stalling speed. Yeah. When an airplane comes to land, lift produced must be nearly equal to the landing weight. Let me ask you, let's actually talk about this a little bit. So the lift, we are saying the lift produced must be equal to the landing weight when we are landing. But when we are landing, we don't really need to have any force in this direction. We can actually, weight can be higher than lift because we want to go towards the Earth. We want to go towards the surface of the Earth. Why do we say that the lift still needs to be equal to weight?
So you don't destroy the landing gear and you crash instead of land?
That's
slower descent.
That's a very good point. Essentially, if well, let's see if there's any other. Is there any other person, a student, who wants to have another opinion? So, what was your name?
Rafael.
Rafael. So Rafael here said that if weight is higher than lift, what is going to happen is that when you get close to the ground, when you actually touch the ground, you are going to crash your landing gear. If you don't crash the whole plane itself, the least you would do is to crash the landing gear, which is true, which is definitely true, because we are moving towards the Earth's surface at a very high speed. But this statement is true even when you are not that close to the ground, even when you are like a little further away from the ground, right? the lift still needs to be equal to weight. Why is that the case? Because when we get closer to the ground, we can still increase the lift, and we can avoid that, right?
If the lift isn't at least equal to the weight, your plane's gonna crash.
It is going to lose its altitude, right? But
Yeah,
doesn't
it's-
necessarily crashes.
Well, yeah.
But you are moving in the right direction, though. Yeah. Do you want to add anything else? Yes.
I think the point of that is to have a gradual balance as you're decreasing altitude, so that way the landing is much smoother, rather than it being more of an abrupt crash.
A smoother landing is actually a very important point here, right? That's actually that is the point. That's the point I wanted to do. Do you want to add something? No. So the control, the smoother landing, control is the very important point. If you don't really have the force balance, you're going to lose the control. You're going to lose your control on the aircraft, right? And you never want that to happen. You always want to have control, right? And so we have two important parameters here: the takeoff velocity and touchdown velocity. And we're going to see how to calculate these velocities. And as I said, I probably will. Really depends on how much work you need to add. You need how much more work you need to do to be able to calculate these. But I will probably add these to your lab reports. We will go over the equations here right now. We define the takeoff distance, and this is something I will ask you. I may ask you to calculate. We define the takeoff distance as the horizontal distance covered by an airplane from the start of the run till it climbs to a height equal to the screen height. What is the screen height? It's just a convention in the aircraft industry, in the aerospace industry. That's 15 meters. So whenever your height is 15 meters, it's called the aircraft height, and the distance it takes from 0 velocity to 15 meters height is going to call the takeoff distance. We have three different parts of this takeoff distance. One is the ground run, in which you are completely on the ground, and the other one is the transition, when you start transitioning from the ground, start taking off, and the third one is the climb, when you reach the 15-meter screen height. And let's actually go to the equations. We'll come back to this later. Yeah. So we will talk about equation of motions in a more detailed manner when you take a flight and orbital mechanics course. But here we will just have a very small discussion on this. What we want to do here is to write the force balance in different directions for the plane, right? So what are the forces present in the x direction? You have thrust, you have drag, and you also have, what is the other force that is present in the x direction?
During takeoff? Friction.
Friction, right? The ground friction, right? Which is the friction coefficient multiplied by your reaction force, ground reaction force, right? So those three forces is going to be equal to m multiplied by m. That's the second Newton's law. Really simple. M can be calculated by weight divided by the gravitational acceleration multiplied by your acceleration. And the y direction, we are not moving in the y direction yet, so that we are not accelerating in the y direction yet when you are doing the takeoff. So all of that is going to be equal to 0. So lift plus the ground reaction minus the weight is going to be equal to 0. You play with that a little bit, and then you can find the ground run distance, which is going to be equal to the integral of W over g, weight divided by the gravitational acceleration, integral of 0 to v1, v dv divided by t minus d multiplied by the friction coefficient minus W minus f. So all of these, you can actually assume all of these are constant. Then you are doing this calculation. But one thing that is going to be the hard part for you guys when you are working on your lab report is determining this VDV. So we cannot just simply assume that V is constant, because it is changing, it is accelerating from 0 to a V, right? So we need to have that distribution. If I could find a way myself for you to export that like formula based on the distance or based on whatever, I will ask you to calculate the ground run and the takeoff distance. But if not, I will just leave it at that. So, and we also have the ground run time, which can be calculated using this formula. Keep in mind that this formula only gives you the ground run, not the takeoff distance. We still need to find the transition distance and also the climb distance. Transition distance, same thing happens. You just have to write an energy balance here. We can definitely write a force balance, but that is not going to be very helpful to us. You can write an energy balance here to find the transition distance S of t and transition time T of t. And eventually we can calculate the climb distance, but you have to be given an angle of climb to be able to calculate that climb distance, which you will be given. Or you can actually export that from the software we are going to use. And you add all of these three distances, you have the takeoff distance.
So when the airplane is 50 meters above, it's considered takeoff?
Yeah.
Oh.
So you have already taken off. Yes.
Is that height going to be the same for all classes of aircraft?
Yes. That is essentially based on that 15-minute tells you that you have surpassed the average height of the buildings and trees and everything, right? So you are already in air. That is not necessarily true for everything, but there's an average. It's just a convention, right? So it doesn't really matter what aircraft you're flying.
Didn't know that.
So like once you're over the 50 meters, you're considered to be in flight, and if you're below them, you're considered to be still on the ground.
Yeah, in air.
Technically, your wheels aren't touching anymore.
No, they are not touching anymore, but you are technically considered on the ground. Yeah.
Okay. Yeah.
Yeah. And that the reason is so you can still hit an object.
Yeah.
Right?
Makes sense.
I mean, you can hit an object even when you're 1 kilometer. I mean, not 1 kilometer, about 15 meters above the ground, but those are very rare objects, right? Like a skyscraper or something. Right? Any questions so far? Okay. Actually, we talked about this a little bit. We have different types of takeoff mechanisms when it comes to planes. One of them is when these are smaller aircraft usually, when your tail actually goes up a little bit. When your tail takes off, then you can just use the pitch up mechanism, elevators, to be able to be airborne. The landing mechanism is essentially the same thing. We have the same force balance system. We have the same for transitional part, or installed here is going to be the flare and float part of the distance. You are going to have the energy balance, exactly the same things. You already know the angle of this gamma angle that we had here. Angle of climb is going to be angle of descent. You already know this. This is based on your own determination. You have to determine this yourself. and flying. So you can exactly use the exact same analysis, exact same equation to find the landing distance. How much does it take off? How much is the length from 15 meter screen height to velocity 0? It just moves in the other direction. And at some point, the difference is going to be that you are going to turn off your engines, right? So you are not going to include thrust in your calculations. Any questions here? Yeah, I'm still debating whether to include this in your lab reports, but you definitely have to know it. Anyways. Let's just stop here. Let's talk about what we're going to do in the next lecture until lab 2. In the next lecture, we of course are going to continue this discussion. But what I'm going to do, either in the next lecture or the lecture afterwards, is that I'm going to teach you how to use the Playmaker software, which is a software you're going to use to modify your aircraft. Also, we are going to use an analytical software called X-Foil to calculate the coefficient X-Foil. I'm pretty sure you haven't seen that software. It's a very old software. It's a command line based software, so you have to type in your commands. Yeah. We're going to learn how to use that, and we're going to use that in our analysis of an incompressible aerodynamics. Yes.
The lab is tomorrow.
No.
It's next week.
Next week, yeah. The labs start next week, yeah.
Oh.
Yeah, there is no lab tomorrow. Make sure you check the Blackboard before going to any lab. So the dates of the lab are already on the syllabus, but if something changes, I will send you an email, but it will also be updated on the Blackboard under the course contents, right? You should see the location of each lab, and the location, someone actually asked me this. Was it you? Yeah. What was your name again?
Patrick?
Patrick asked me this, actually. I think I forgot to mention this. There are 2 classrooms listed as the location for the labs, not the lecture. And those are just random classes, right? They just chose these random classes. Those labs don't really happen in those classes. Right? And the location of the labs will be announced on Blackboard. So you have to go to Blackboard, check the course contents, and then you know where to go for the labs. Most of them will be 300 mains based. That's it?
Is the next lecture Monday?
Pardon me?
Is the next lecture Monday or Friday?
Next lecture is Monday. There is no lecture on Fridays.
Have a good weekend.
You too.
Oh, no, they're on.
Have a good weekend.
You too.